this for the rest of my career. Because I think maybe there's a camera back there. Do you guys know that? Yeah, I think back there's a camera, right? There's one in every lecture hall. I can actually like show you the Okay, next time, that's what I'll do for the video. I'll show you that you can see yourselves. Yeah, but technically all we have to do, I think, is tell someone to record the lecture and the lecture can be recorded. It should be done by policy, in my opinion, but I'm not the boss here. So are we in fact recording? I can never tell. Yes, okay, so that circle with a square in it means we're recording somehow. Okay, so today we're going to talk about algorithmic complexity. So yesterday we ended with a discussion about how to compare various sorting algorithms, right? Because we came up with 3 of them: selection, insertion, and bubble. And now we want to have some idea about which one is better than another in individual cases. So I'm going to have to show you some math. And you should get used to this because computer science and math go hand in hand. So we don't really want to talk about the efficiency of an algorithm. Efficiency is the wrong word, right? Efficient means you're just doing something in a smart way. What we really want to measure is the complexity of an algorithm. Now, it's true that programs that are more efficient, no, that's not true. You can inefficiently program something with a better complexity than another algorithm, right? So like efficiency is really a term about implementation. I've given you a set of instructions in pseudocode, and how well have you written them into the compiler? Like, did you use linked lists when you should have used like regular lists? Anyways, efficiency is not the right word. Complexity is the thing that we want to use. So we want to measure the complexity of our various sorting algorithms. So what we're going to do is we're going to pick some operations and count them. And the number of operations that the algorithm performs, we're going to call the complexity of that algorithm. So if we looked at our sorting algorithms and say we just measured the number of times two positions were swapped, right? All of our sorting algorithms have to swap positions at some point. So that's a good candidate for what we could count in order to define the complexity of those algorithms, which we may do later. We usually denote, so like what we really want to know is, if you double the size of the input, what is the effect on the timing, right? And we want to codify that relationship mathematically rather than one that's like dependent on the machine. Okay, so I'm just going to give you a sample of how we're going to measure these complexities. So here's something that's going to have a linear time complexity, and I'm going to specify what that means. So and these are just sort of functions that don't do anything. They're just for exposition. So if I have a function which takes a list of length n, and then just walks that list in a while loop rather than a for loop, right? So it just declares an index as 0, and it increments that index n times. So let's ask ourselves how many things are done, like how many operations are done at each line of this algorithm. Well, let's say to set a variable costs, okay, 1. We've done one thing, we set a variable. We set another variable that costs 1 again. We have to, so this while loop is actually doing work, right? At every iteration of this while loop, it has to make this comparison. Right, so how many comparisons are we going to do if we walk the list of length n? Well, we're going to do n many comparisons. Now, it turns out that we're going to do exactly n many iterations of this loop, which means that this index counter is also going to be incremented n times, right? So this line here is doing n many additions, okay? So we can sum all of these counts together to get, oh, sorry, this should be 2n plus 2, not 1. Turns out it doesn't make much of a difference, right? So we do 2, so given a list of length n, the complexity of this algorithm is 2n plus 2. Right, so that means that there's a linear increase in the complexity depending on the size of the input, right? And we actually don't care about the particulars of the, like we don't care about the coefficients of the polynomial that represents the complexity. We really only care about the order, right? So you guys took calculus, right? Do you know when you're doing limits and we give you like a rational polynomial, and you're told just to find the highest degree, right? Because coefficients and stuff don't really matter like out there. It's basically the same for this, right? I only care about the relationship being linear. I don't care specifically of like what relationship that is, at least at this level. So I use this big O of n, okay? So big O of n is a symbol that basically says this is the category of all linear equations, right? So there's two ways of thinking about this. I actually don't like using this as equal. I think this is an abusive notation, but that's what we do. I like regarding as O of n as all possible linear equations. And then this is among all possible linear equations, right? But the real definition is this one. Now, don't be scared. Remember, I showed you these symbols a while ago. They're just fancy symbols for things that we say in English, right? So we say that the function f of n is big O of g of n, and write fn is equal to big O of g of n when? I have to take a sip of my coffee because it's a serious statement. There are positive constants, c and k, such that for every n greater than or equal to k, f of n is bounded by 0 and a constant c times g of n. Now, this is going to become much more clear if I show you an example. But this basically says that a polynomial is bounded by another polynomial if there is some constant that you can multiply the second polynomial by, at which there's a point in the domain where the one polynomial is greater than the other. Again, example. Okay. Examples. 2x squared plus x plus 1 is big O of n squared because for all x greater than 2, 3x squared is bigger than 2x squared plus x plus 1. Right? There is one polynomial of the same degree with a higher constant which exceeds it. So I guess if I were to draw this, right, you can have two, sorry YouTube, you can have two curves, right? This could be x squared, and then you could have another one, maybe I should call this half x squared. And then you can have another one which is like x squared, okay? Where this is your point n, right? So basically if you draw your one polynomial, and then you draw another polynomial that has only its leading term, and you can stick constants onto it. And if you draw the function, you should see one point in the function where the new function exceeds the old function everywhere. Don't be too concerned about this. I even sort of regret showing you the formal definition. We're not testing you on this, right? This is just a sample of what is to come. You're going to take whole courses where you have to determine the algorithmic complexity of functions. It's very important. Right? Basically, as computer scientists, this is the only thing that you're going to be concerned with. Developing, because you're going to have to develop a new algorithm and then somehow demonstrate that that algorithm is better than the current algorithms. And you don't do that by timing. Well, you can time, but that goes in an experimental section of your paper. Right? I say, okay, that's nice that practically speaking you have a good algorithm, but what is the complexity? Right? So, and I hate it. I hate algorithmic complexity. I'm terrible at it. For the same reason I'm terrible at analysis. Has any of you ever taken an epsilon delta type of proof course? Yeah, you're in one? Yeah, you'll need that for algorithmic complexity. So I hate complexity for the same reasons I hate epsilon deltas. Okay, let's do another one. X cubed minus the sine of x is n cubed. Why? Well, this is a two-step process now. I know that x cubed minus sine x is always smaller than x cubed plus 1. Right? Because the smallest that sine can be is minus 1. Right? So this is definitely bounded. Right? So this term is bounded by negative 1 to 1. Right? So I just replaced it with 1 of its extrema. And this is always less than 2x cubed for x greater than 1. Right? You can test it if you want. But it's not hard to see if you move this x cubed over to here that x cubed is greater than 1 for x greater than 1. But again, so just all you need to keep in your mind is you have the plot for the runtime complexity of your algorithm, and it has a degree. Like maybe it's a cubic. You have to find another cubic with some constant so that there is some point on the graph where this exchange happens, right? Where your one curve is bounded by the other, right? So anyways, here's your sample for big O notation. we're not going to test you on it. And if we do test you on it, it's going to be a question like this, nothing to do with the high level of math. Okay, so I want to determine the complexity of this algorithm. Let me move it so we can tag it as we do it. Now, hopefully, this will let me paste in the spaces. Great. Okay. So let's now go through this and try and figure out the complexity of this algorithm. Oops. Okay, let's start with the easy ones. How much does it cost to set a variable? 1. Constant time, right? How much does it set to set this variable? This one? Okay, so now we have a list of length n, and we're playing the same game. We're just sort of walking the list twice, right? We're going to walk the list in the outer loop and walk the list in the inner loop. So how much does this outer loop cost? N. So that means how much does this cost? No. N. So I'm doing something that costs 1, but I'm doing it n times, right? Okay, so n squared, right? I'm doing something n. There's n comparisons that happen here, but they happen n times, right? Same for this. This is I set something once n times. Well, I set something once n times, but then I do that n times, right? Because it's in the inner loop. And then this actually just gets 1 constant time times n, right? So what happens if we add this up? We get 2n squared plus 3n? Is it? 1, 2, yeah, 3n plus 2. All right? What's this big O of? Perfect. Do you want to actually find it? I'm pretty, like 3n cubed is going to be bigger than this for sufficiently large n. Like for polynomials, these are very simple type of complexities. Do you want to check? Okay, I can check. Can I plot two things in Google? Plot x squared and x. Aha, I can do that. Yeah, what's the one that you guys like using? Desmos. I don't know why I say that with such contempt. Oh, Desmos. 2n squared plus 3n plus 2. And, I don't know, 3n squared. Won't let me do it like that. 2n squared plus, okay. What? Oh, maybe it doesn't like the n, all right. Maybe I have to put some y's. Oh, that's the rub. Okay, so let's see. How come I can't make this bigger? Bigger, bigger, bigger. Okay, so the blue curve is the runtime of the algorithm we just measured, and the red curve is the polynomial that bounds it eventually, right? So it eventually bounds it. So this should be true after maybe like 4, right? So, but this is what we're looking for. We're looking for a curve that's going to bound the curve asymptotically. So sometimes you actually hear this referred to as the asymptotical complexity, because they're concerned about what happens as n approaches infinity. Okay, cool. Maybe I'll just leave this open in case we want to do more. Okay, so this ended up having quadratic runtime complexity, which is already pretty crap, right? We saw this with our lists, right? We determined somehow increasing the length of our list by 10 had an effect on the runtime by about 10 squared. Right? You shouldn't be surprised then that we can do this at the end of class, that the algorithmic complexity for all of the sort algorithms that we devised or implemented are n squared. N squared, n squared, n squared. If we don't get to it, you should go into the code and see if you can figure out why. Like, go play this experiment. Let's do one more. Actually, let's do two more. I think I actually missed one. So let me do. Okay, I'm going to skip this one for the time being. Remind me to come back to it, and then I'll have to add this to the slides. Okay, so let me think here. What do I want to do? I want to take in L, a list. I'm going to say n is equal to the length of this list. Then I'm going to say my counter is 0 while I is less than 10 to the power of 10. Just increment I. And then do nothing, return. Right, none. Okay, let's go through this and determine its complexity. Okay, so how much does this cost? With enthusiasm. There you go. At least say the things you're sure of confidently. What about this one? What about this one? What about this one? Why? Don't get lazy. Look at the code. There's no n in there, right? 1. Okay, I'll show you why. 10, this is 10 to the power of 10, right? This is also 10 to the power of 10. Okay, which means that in the end, what do we got? We got 10 to the power of 10 plus 2, which is just O of 1, because it's a constant. What polynomial bounds this everywhere? I don't know. 10 to the power of 11. Right? It's just a line that's higher than this line. Don't look so perplexed. Ask me a question. Does the runtime of this change depending on the length of the list? Yeah, you. Well, do I do anything with the list in the code? Is anything done with L or N in the code? No. So like, yes? No, if the list was limited to 10, then it's constant. Yeah, then you're like that's now become a finite list. Now everything's O of 10, right? It's at most 10, right? So I don't care that you're shrinking the list. I'm trying to make an upper bound on the timing, right? Okay, so we can do upper bounds, we can do lower bounds, and then there's like this sort of thing that cuts it in the middle. But for the time being, like really what we care about is the upper bound of the runtime, right? Because like we could always be wrong, right? I say, oh, bubble sort is quadratic, and you give me a sorted list, and it like returns after the first iteration. We don't then go conclude from that bubble sort is the bee's knees, right? So it depends, right? This is why complexity is tough, right? You have to think of the average case over all possible inputs, right? You need a lot of math to do this. But okay, so back to this. This is like I can bound this with a like this is going to finish after a certain number of iterations every time, right? It's not changing depending on the size of the input. I know it seems like we're doing a lot, right? That I'm doing like something 10 to the power of 10 times, but that's still a bounded number. That's still a constant number. So this is O of 1, right? Constant runtime complexity. So I'm going to have to add this to the thing. Add to the slides. You dope. Okay, this is the one I wanted to do next. Let's just get rid of that. Go away. Okay. I want to go through this, but I actually want you to think for like maybe a minute or so. So why don't you stare at this? And I'm going to pace from here to there and back. Yes?
What is the index plus equals 1 also?
Oh, I don't know. How about that? It's because this isn't carrying spaces properly. Yeah. Okay, so can I begin my pace? All right. I'll look very perplexed. It helps to try and figure out what this is returning. Okay, let's do the easy ones first. Who wants to volunteer? 1. 1. It can't be 1. There's definitely... well, okay, so you're technically correct because you've bounded it, right? But... so who will be better? Like, so this is another problem with algorithmic complexity. You can overbound and still be correct, right? But obviously, we want the least upper bound, right? We want to get our estimate as close to the actual thing as possible. This is called the infimum. It's either the infimum or supremum. I always forget. One is the least upper bound, and the other one is the greatest lower bound, right? Yes. Nope.
Yeah, because like it's like while 2 to the, if it's false, it'll say 2 while to the 0.
Okay, the list is of length 1,000,000, right? So I'm going to be able to go 2 and then 4 for sure, right? So it's not the case that it only runs once, right?
Is that infinite?
No, of course it's not an infinite loop.
Because like it will always be true.
Okay, so like I don't understand. If I were to take this out, you guys would have no problem, right? So what is it now? It would be n, right? Okay, so if I put this back, I'm now increasing, like this is now moving faster, right, in value. So it has to be less than n, but not constant, right? So it's not a polynomial anymore, and I'll give you that hint, right? Okay, let's ask ourselves some questions. If the length of the list is 2, how many iterations do I get? You guys forgot how to program? Right? I'm counting, the index is moving by powers of 2. Right? The index goes 0, sorry, not the index. The thing that we're comparing moves by powers of 2. So we get, the first one is 2 less than the length of, oh, I guess the first one is 1 length than less than the length of the list. Is 1 length less than the length of the list. 4, 8. You got it?
Is it a log?
Which one?
Log base 2
Of what?
of the length of the list.
Everyone with me? So if you want to answer the question, when is 2 to the power of x less than n? This is when log base 2 of x is less than log base 2 of n. Yeah, simple calculus, or not even calculus, simple arithmetic. Please tell me everyone's okay with this, yeah? I'm looking out very concerned. Okay. So this is awesome, right? If you can introduce a log to your complexity, that's great. Why? Yeah.
Logs increase slower and slower over time. So as your list gets arbitrarily large, there's very minimal difference at some point.
Sure. I'm gonna say it like a 6-year-old. This thing log takes really big numbers and makes them tiny. Right? Think about what log is doing. You give me a number and I count its digits, and that's what the log is. So you give me a number that's like order of billions, and you're getting something back that's like, how many zeros in a billion? Yeah, you get something about 7. Right? You're going to take something from 1 billion to 7. Right? So introducing a log is crazy good. So the best sorting algorithms we have, well, okay, not the best, but we have sorting algorithms that you will already be able to understand that operate in this runtime complexity. N log n. Now, we can do 2 things from this point. We can either go through insertion, selection, and bubble and do the complexities of them, or we can write a new sorting algorithm that has this runtime complexity. Okay, so we have his vote. Anyone second? New? I know you wanted to see the runtime complexities, yeah? Okay, compromise. We'll do the runtime complexity for one of them, and then we'll do a bubble sort. Okay, so you can, which one would you like? Insertion, bubble, or selection? Bubble. Where is bubble sort? I think I put it in here. Bubble. Bubble, the bubbles, the bubbles. Okay, thank you for picking bubble because it's all of this is in one place, so you don't have to jump between functions. Okay, so let's just assume the list is of length n. I'm not actually going to declare it as a variable. Whoops. So let's go through here and try to determine what the runtime complexity is. Yeah. So I'm just going to do this. I hope you guys are thinking. Let's do it. Easy. Ooh. While loops make things a little bit hard. Okay, so now we have to start thinking more critically, right? Because now we need to think at higher level about what this algorithm is doing. Right, so when we bubble, remember we're scanning a list. So if we scan the list once, how many elements are in order? 1, which means how many times can we scan that we're sure the list is sorted? N. Okay, so we're going to remember, I'm not saying this is doing n iterations. I'm saying that this will at most do n iterations. You follow? Okay. So this will at most do 1 operation at most n times. Okay, so this is going to do k in range. So basically, they're setting k once. This is happening in a loop, so that happens at most n times. And we have to go to the length of the list, which is again at most n times. This is going to happen, does one comparison once, n times. Does this swap once, n times. And does the same thing here. 1. N times. This is really the only thing I care about. That's swap. If we counted this swap in every sorting algorithm, that would give you n squared complexity each time. Right? You normally don't have to count every addition, division. Like there's normally one thing that you're going to know is going to be the thing that's doing all of the work. Right? There is a reason I'm saying, suppose we restrict ourselves to this like atomic way of moving on lists. I gave you like 1 operation on lists, and that's the thing that we should be counting. Okay, in any case, what do we now conclude the complexity of this is? Okay, so 4n squared plus what? 2n plus 1, which is O of n squared. Okay, so this is has quadratic runtime complexity, which is bad, right? Because I've already shown you, what was it? Was it 10,000? Anyway, it was like I couldn't sort a list of 100,000 in less than like 20 seconds, which is pretty dismal. Because 10,000 isn't very big for computer scientists. Like numbers like 2 to the power of 32 are big numbers for computer scientists. Okay, so now you want to do... Okay, so you play this game with insertion and selection. In both of those cases, you should determine that there's a quadratic runtime complexity. So I'm going to close this. Don't save it. I'm also going to get... This has to be... I'm going to save this somewhere else. Add to slides. Okay, go away. Okay, big caveat here. Caveat. Whoops. This is not testable and uses advanced techniques. Okay? So, again, not testable. Please don't Piazza the crap out of this. I don't understand merge sort. Okay, so that being said, this is just to show you what's to come, because I'm going to have to write a piece of program recursively, which hopefully you'll also be comfortable with. So we're going to write something called merge sort. I'm not going to implement it efficiently, right? But it is going to have the complexity that we want. So it's going to take a list, L. I'm going to say X is, which is a list. What is happening? Why am I getting 8? I don't want 8. I want 4. Okay, so this is no longer going to be an in-place one for reasons I'll tell you later. This is going to return a list. This is going to perform out of place sorting, ascending sort. Okay, so remember how I restricted you to a certain list operation. One of them was you can find the largest element in a list, you can insert an element into a sorted list, or you can swap to adjacent cells. I'm now going to restrict you to another operation, merge. So merge is an operation where you take two sorted lists and you combine them into a super list that's sorted. Right, so that should be easy to perform, right? You just, well, let's just write it then, okay? I think this is screwing up my tabbing. Nope, 8 tabs. Okay, you know what? I'm just going to kill this. Perfect. Okay, so let's do merge. That takes 2 lists. And this should return another list. So it takes 2 sorted lists. I should make that a capital. Sorted lists, x's and y's. Returns a new list, z's. That is the sorted list of x's plus y's. Return z's. Okay, so how can I merge 2 lists now?
Make 2 indices and iterate while getting this, make one index for x's and one index for y.
I hate indices. I'm going to do this instead. I'm going to reverse the list so I can pop. Okay, and what I'm going to do is while if there's something in x's or y's, I want to do something. Right, so I need to perform something while I still have elements left. Okay, so I'm going to say x is equal to x's dot pop. If x is else, I need to set this to this. Am I sorting in ascending order? So float inf. Okay, so this line basically says pop the thing off x's, but I had to put some decoration around it to say, look, don't pop something off if it's empty, because that's going to throw an error. So I'm saying if there's something to pop, pop it, else just set yourself to float infinity, which I think is the right constant to use here. So what do I do here? Oh no, maybe I shouldn't be popping. Okay, maybe I changed my mind. I still think this is okay. Because I'll just index from the back. Okay, so if the last element of x's is greater than the last element of y's, no, less than, then it's the next thing that goes on z's, right? Yeah, z's append on x's dot pop. Although we're going to have to fix this. This already assumes something is in x. Else, actually I can still do this. If y's is less than x's, then z's dot append y's dot pop. Right, so I took the 2 sorted lists, I reversed them just so I could use this pop, and I'm basically saying which one's smaller. Okay, take it and add it to the list, but throw it away. So the 2 lists that I took in should be shrinking over time. Again, this is like a super inefficient way of programming this. Okay, so now I have to make sure that, yeah, what's up?
You have to add some of them runs out, you'll stop iterating.
I'm saying iterate while one of them is non-empty.
Yeah, so like now you have to like add another loop that like takes the remaining list and just pops every element.
This will run if anything has an element in it. This is not going to stop when one of the lists empties. This is an or in the middle of this, not an and. If either x's or y's have an element in it, this loop is going to run. It's an or, not an and.
Right? Then one of them runs out, then you're gonna get there.
How?
Because you can't compare, like you can't index something.
Well, that's exactly what I'm going to fix now. Right? That's why I left myself a note saying that this is broken. So we're going to do something like if x is and. Right? If there's something in x's, right? So this is where we're going to exploit the short circuit nature of the and. Right? So if there's nothing in x's, it's not going to bother evaluating the second half of that, which means that there's no index error is going to throw. I'm trying to show you some tricks to keep your coding a little bit more simple. But this is going to do the comparison safely, right, by first making sure there's something in x's. Same thing for here. These are just some coding tricks to help you along the way. Right? This should already work. So let's see. How much time do I got? 8 minutes. I'm not sure I'm going to be able to do this in 8 minutes. So let's see. Can we merge 1, 2, and 3, 4? Flies. Oh, I see what you're saying now. I owe him an apology. Yeah. Yeah, these comparisons are going to break, which I just found out. Okay, so how do I have to fix this? Okay, so I guess we can have one loop that just assumes that they're full, right? And then I have to do another loop. Okay, so but at the end of this loop, one of the lists is going to be empty. Okay, so all I have to do to z's is extend it by both. As soon as one list is empty, I just sort of paste the rest of the next list on. Right? So let's see if this works. Huh? Oh, come now. Line 14? How? Oh. Okay, I shouldn't do this seriously. Serially. I should do this seriously. Oh, why? Why? Z is wrong. Oh. Because I flipped the list at the beginning. Okay. You guys should definitely re-implement this using indexes because this is bad code. I'm kind of embarrassed for doing it, but it works. Right, I can merge. This thing can be longer. Right. Let's try to do something non-trivial. So maybe this is 3, 8, 9, and this is 1, 2, 3, 6, 10. All right, this is getting quite embarrassing. I actually threw an infinite loop somehow. Okay, let's try to do this again. Let's try to at least write the merge so I can redeem myself. Let's do it your way. So I'm just going to do it properly. I'm going to create 2 indexes here. One for the x's and one for the list. And while
I is less than the length of x.
I is less than the length of x's and j is less than the length of y's. If x's at I is less than y's at j, then I want to say z's get appended, and I know it's not there. I want to append x's at I, and then I want to increment I. Elif Oh, I think I could just do an else, because I have to catch the other case anyways. Else we append y's at j, and then increment j. And then after we finish this, then I should extend z by either what my I is at or what the y's is currently at. Let's see. No, wow, much faster. Okay, great. I should have listened to you in the first place. Okay, so we have a merge. Maybe in the next 4 minutes I can actually do this. Definition of merge sort. I can't do much explanation. But maybe you can study it afterwards. Okay, so I'm going to do this. If not x's, then if not x's, return x's, right? This is the empty case, empty list. Else, I don't have to put an else. So I'm going to cut the list into 2 pieces now. So y's is going to get x's to the length of x's integer divide 2. And then z's is going to be x's. So this should cut the list in half. Agree? Because I'm slicing. Did I do this right? It's slice. Yeah, it slices right. Okay, and this is the part that may confuse you guys. I'm now going to sort y's like this. And then I'm going to return the merge of this. Now let's think just like sort of logically if this sort of makes sense. I'm saying give me a list, cut those lists in half, sort the lists, and then merge them, right? I know how to merge 2 things. That's the thing that you allowed me. Let's see if this works. If not, I'll feel really bummed because this should be something that's kind of cool. Merge sort. Not now. Yeah.
If length of x equals 1, then return x.
You think I need that case?
Yeah, because the minimum sorted list should be the single.
Okay, I'll put another one, but I'm not sure. I shouldn't have needed 2 base cases. Oh, okay. Well, maybe it worked. Like magic. Whose mind is blown? When the first time I saw recursion, it blew my mind. I was positive it shouldn't work. Right? But it works. Right? I wrote a sorting routine assuming that using the routine that I was writing at the time. Right? So who knows what the principle of mathematical induction is? Okay, so the principle of mathematical induction and recursion, twins basically. Right? If you can write an inductive proof, you can get a program. All inductive proofs are programs, and all recursive programs are inductive proofs. But anyways, give this a little bit of thought, and we'll discuss it a bit more on Friday if you guys have any questions. So you guys have a good day.